Hello everyone. So we're going to continue on with our integration and today talk about definite integrals. Now remember a couple of notes ago that we briefly discussed that if you look at a function f of x and when you integrate under the curve, this gives you the area under that curve. So we mentioned this briefly, but we're formally going to define it now, that the area underneath this curve, we can split it up into multiple intervals, okay, where the width of each one of these little rectangles is going to be called delta x, where delta x will be equal to whatever your last point is minus your beginning point divided by the number of rectangles that you have. So that delta x, we can express it as b minus a over n. And then we can approximate this area by taking the area of these rectangles and then adding them all up. And remember that we used sum notation, which looks like this, which just means I would say the area of this one plus the area of this one plus the area of this one, so on and so forth. So my sum, I'm going to have one rectangle to n rectangles, where the height of these rectangles will be f of xi, where xi is whatever rectangle you're at, times the width, which is delta x. Now this is an approximation. The larger your n is, the better your approximation is going to be. If we look at the limit, as we have infinitely many rectangles, then we're going to be able to actually find the area. And this is how we define something called a definite integral. If we have some sort of function that's continuous on some closed interval a to b, remember if we don't have a certain interval, these are called indefinite integrals, and we need to have a constant of integration. But if we're looking at a particular interval, and then we look at the limit of the Riemann sum as n goes to infinity, and remember this is what the Riemann sum was called, okay? It's just this expression to approximate area. Then the definite integral from a to b is denoted by, we use our integral symbol, from a to b, where these a to b are bounds or limits of integration, whatever the function is we're integrating over, and the dx tells us what variable we're integrating with respect to. And this is what the limit, as n approaches infinity, of that Riemann sum means. Okay, so we have this new notation to make this much easier. Okay, so this is equivalent to this. Okay, now notice that, if we go back to this picture, remember we talked about that, say I'm drawing these rectangles and I put a point on the left side of the rectangle and I draw a line here to get my height. That's going to under or over approximate, because if I put the point on the right side, then my rectangle is actually taller than the function. If it's on the left for this particular rectangle, it'll be shorter. So approximations, depending on how you put this point to make the top of the rectangle, there's going to be some error involved. And there's three main ways that we can divide our intervals. Okay, so let's say that we divide our interval into a few different rectangles. Okay, so let's say we'll have a rectangle from x0 to x1, x1 to x2, x2 to x3, x3 to x4, and then x4 to x5. So if I put my point on the right side, so say I put my point here, and then I draw a line, that's going to be the top of my first rectangle. If I do the same thing for all of these, okay, the tops of my rectangle look like this. And for the last one, because it's at the very bottom, okay, we don't even have a rectangle there. The area for that one is 0. But if I do the same thing down here, but instead of putting the point on the right side, I put it on the left side of my rectangle. So the first one, again, would actually have 0 area, because my left point for the first rectangle is starting at 0. But for my second one, if I put my point here and then go across, put my point here, go across, here and go across, and then here and go across, these look a little bit different. Now, if this curve is symmetric, the right endpoint or left endpoint on how to draw the tops wouldn't matter. But if your function wasn't symmetric, one approximation may be better than the other. Another thing we could do is if, again, we split up this curve into multiple rectangles, an approximation that would be slightly better would be if we took a midpoint. So instead of going the right side or the left side, I take the middle point. And when I take the middle point here, and then I draw my top, so middle point, draw the top here, middle point, draw the top here, middle point, top is here, and then middle point, top is here, this approximation is going to be slightly better than both of these two. So depending on how we draw points, our expression to approximate our area will be slightly different. So if I'm looking at this one right here, for the right endpoints for my first rectangle, the top of that first rectangle is going to be defined by whatever f gives me if I plug in x1. And so the area would be that value times the width. And then we're going to have, for my second rectangle, the top is going to be defined by f if I plug in x2, delta x. For my third rectangle, if I do a right endpoint, I'll have f of x3 delta x, then f of x4 delta x, plus f of x5 delta x. But if I'm looking at the left endpoint, I'm not starting at x1 this time. That first rectangle depended on f at x0. So I have f of x0 delta x, and this time my second rectangle, this time that'll depend on f being applied at x1. So then the area of that second one would be f at x1 times delta x. And then our next one would be here. So f at x2 delta x, and then we would have f at x3 delta x plus f at x4 delta x, and that corresponds to our last rectangle. So the point that we're starting at, depending on the left or end right point, the expression will be slightly different for our Riemann sum. Now if I do midpoints, this time the tops of each of my rectangles will depend on these m's. So the area of the first rectangle would be f at x at m1, we'll call it delta x, plus f x at m2 delta x. And then we keep going until the last one, f at x at m5 delta x. Okay, so these pictures will look slightly different. But again, these are just approximations. We'll do an example so you can see how we consider more and more triangles, our approximations will get better and better. Okay, so say we have this function. Now it turns out that this function, this 600x minus x squared, this is actually going to be symmetric. So it wouldn't matter if we did the left or right endpoint. So we're just going to pick the the right one actually. And what we want to do is we're going to split this up into 6 subintervals. And then we're going to approximate the area. And afterward, then we'll split it up into 12. And then we'll approximate the area and see what we get. So if I'm splitting this up into 6 intervals, and my x is between 0 and 600, how wide are these going to be? Well, you may just see quickly that, okay, well, the first one would be here, the second one would be at 200, the third one 300, 400, 500, and 600. So in other words, I'm starting at 600, my initial point is 0, and I want to split it up into 6 subintervals. So this is justifying that that width, that delta x, is going to be 100. Okay, and now because I've decided to put a point on the right side of each of these rectangles, okay, the tops are going to be here, 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 and then here. So my area for this first rectangle here, I'm going to find it by going, this value is going to be f at 100, and then times that width. Then it will be f at 200 times the width, plus f at 300 times the width, so on and so forth. So if I wrote that in sum notation, I'm going to have 6 rectangles in total. And because I'm doing right endpoint, I would write this as f of x1 delta x plus f at x2 delta x plus f at x3 delta x plus f at x4 delta x, f at x5, and then finally I'm going to have a sixth one. Okay, and what that means, and something we can do to make it easier to write down, is because they're all multiplied by delta x, I'm going to factor that out. But the top of my first rectangle, we're going to have to plug in 100. Then we'll have to plug in 200, 300, 400, then 500, and then 600. And then we can multiply all of them by delta x. Okay, so if you actually plug in these values, we would end up getting, for the first one, we would get 50,000. And then we would get 80,000. The max is going to be at 90,000. And then due to symmetry, we're going to have 80,000 again, 50,000. And this last one here, without even plugging it in, I can see that it's going to be 0. Okay, because that curve goes back to 0. And then what is my delta x? My delta x is 100. So if I add up all of these and then multiply by 100, I'm going to get 35 million as the approximation for my area. Okay, but now, what happens if I instead split up my interval like this? So before we had 6. Okay, so before we had this many rectangles, but now I'm going to do it for 12. So I'm again going to split these up into, an additional 6 rectangles. And again, I'll just choose to do the right endpoints. You can do left or midpoint if you wanted to. So the top will be here and then here. We'll draw the tops of all of these. Okay, and we can already see, just look at the difference above and below f if I have 12 compared to 6. This is going to be a much better approximation, even though it's still an approximation. Okay, so this time, to justify that my width is 50, I'm starting at 600. My initial point is 0, and I want to split this up into 12 rectangles. So 600 divided by 12 is 50. And then the area, to approximate it, I'm going to go from 1 rectangle to 12 rectangles. And then I'm going to have f of x1 times my delta x, f of x2 times my delta x, and I would have 12 of these. So f at x12 delta x, is that our starting point? Yep, because the right endpoint finishes there. Okay, so that's all good. And then same as before, we'll factor out the delta x, and then what does this mean? So my first point, my right endpoint, is going to be at 50, and then 100, 150, 200, 250, so on and so forth. So I'm going to have to find out what each of these are. And then we'll plug in the value of whatever f is at that point. And then we'll just add them all up and multiply by 50. And then we'll be good. So f at 400, f at 450, f at 500, f at 550, and then finally f at 600. And then all of that will be multiplied by 50. Okay, so when you actually do that and plug in the numbers, hey, you'll see it on the note posted online, but we're going to end up getting this time 35,600,000 750,000 for the approximation of our area. And it turns out that if we actually looked at the limit as n goes to infinity, so infinitely many rectangles, this, which we can express like this, our definite integral, it turns out that that area is 36 million. So we saw that as we have better and better approximations with the more rectangles that we have until we can get the exact one. Now, a question we need to ask ourselves is, okay, now how do I actually evaluate these definite integrals? And for that, we're going to use the second part of the fundamental theorem of calculus. We'll actually talk about the first part a little bit later. But what this theorem says to us is that if we have a continuous function, and say we know what its antiderivative is, then in order to evaluate that definite integral going from a to b for that continuous function, I'm going to take my antiderivative, whatever that answer is, and I'm going to plug in the top endpoint, and then I'm going to subtract it by plugging in the lower endpoint into my antiderivative. Okay, and sorry, this is capital F, the antiderivative. Okay, so the fundamental theorem of calculus actually tells us how we're able to evaluate these. So let's actually check to make sure that we get this 36 million for our area. So this is a type of polynomial, so we're going to use the reverse power rule. We know that the antiderivative, if we called it capital F of x, well, I have an x to the 1, so reverse power rule, I'm going to have to go x squared, and then I'm going to take that new exponent and put 1 over that out front, so I'm going to have 1 over 2 times 600x squared. And then for my next one, add 1 in the exponent will give me 3, 1 over that new exponent. So I'm going to put this into the integral from 0 to 600 for 600x minus x squared dx. And you don't have to do this extra step to find the antiderivative. Typically what we just do is we'll write it here. We'll put an equal sign and then we'll write our answer. And then in terms of notation, to say I want to evaluate this first at 600 and then at 0, we use this vertical bar. Okay, so this means evaluate at 600 and then at 0. Okay, so in particular, we would have 600 divided by 2. We'll just write that as 300. And then we're going to plug in 600 squared minus 1/3 600 cubed. Okay, so we're going to do all of that, and then we're going to subtract it off doing 300 times 0 squared minus 1/3 0 cubed. Okay, so this whole first one corresponds to the antiderivative at 600 minus the antiderivative at 0. So this whole term is 0 because everything's multiplied by 0. And then if you actually work out the first part, this will give us 36 million. Okay, hopefully you found that helpful. We'll do some extra problems next time, and we'll also talk about the fundamental theorem of calculus part 1. Thank you.